Alright, let's imagine that a molecule becomes a paperclip. This is basically what is asked in this problem. So, first of all, we will need to calculate the kinetic energy of a molecule at 22 degrees Celsius, and then we will calculate the speed that a paperclip would have if it had the same kinetic energy. So this is a two-step problem. First step is calculating the kinetic energy of a molecule at 22 degrees Celsius. So 22 degrees Celsius is what in Kelvin? Well, we add 273 and we get 295 Kelvin. You should be comfortable with this this conversion by now, because I think we've been doing it in most problems. And the temperature in Kelvin is always the one to use in a physics problem. Kelvin scale is the physics scale, is the one that makes sense for physics. 22 only makes sense when you ask your friend, what temperature is it outside? Now, let's calculate the kinetic energy of a molecule in a gas. This is a bit of a tricky question because it's hard to pinpoint the kinetic energy of a single molecule, because in a gas there is a ton of molecules and every molecule has a different kinetic energy. So what we'll do is calculate the average kinetic energy. And we know from the book this is equal to 3/2 times K, the Boltzmann constant, times temperature. So this K is different than this K. Here we have the Kelvin unit and here we have the Boltzmann constant. And the Boltzmann constant is equal to, I'll write it in blue here just to use different colors, 1.38 times 10 to the minus 23 joules per Kelvin. And our temperature is 295. So this is equal to a tiny amount of 6.17 times 10 to the minus 21 joules. The question is, what speed would a 1 gram paperclip have if it had this kinetic energy? Remember what equation links speed and kinetic energy? This is one of the first equations we learned in this book, probably. Kinetic energy is equal to half times the mass of the object times the speed squared. So this is what we will use to find the speed of the paperclip. We can rearrange this equation so that the speed equals 2 times the kinetic energy divided by the mass and square root of all of this. And then plug the numbers in. This is our kinetic energy, and our mass will be 1 gram, or 0.001 kilogram. The reason why we have to use kilograms is because we are using joules here. So to make the conversion between joules and something else, we want to make sure we're using units from the International System of Units. And for mass, that would be kilogram. If all our variables always use the International System of Units, then we know for sure that the units are going to be correct in the end. If you're not sure, then you would need to convert joules into kilograms times meter square. I'm going to write it down here. A joule would be a kilogram meter square divided by second squared. This is what joule stands for, actually. And so if we use gram, we're going to be dividing kilograms by grams, and so there will be a factor of 1,000 difference, which is why it's better to just stick with international standard units. Right, and let's keep going with this here. So I'm going to write it down, 2 times kinetic energy. We will use the average kinetic energy because we don't know which molecules to pick from the gas, so it seems like a good idea to just pick the average molecule. Divide by the mass, 0.001 kilogram, and we obtain the final answer, which is 3.5 times 10 to the minus 9 meters per second. How slow is that? That is, if a paperclip had the same kinetic energy as a molecule. So it makes us realize that the energy scale of molecules is actually very, very small in comparison with objects from everyday life. And this is the end of this problem. So thank you.